Today we're going to have a look at a USB car charger made by a company called Gembird, which usually sells cheap SATA cables, power cables, small switches, hubs, routers, and so on in East Europe. The reason why I bought this USB charger is because it was very cheap. It was about 75% off, so I basically paid less than $2 including shipping. And basically because it should be a bit more quality compared to cheap $1 clones and similar products on eBay. This is a very useful product because you can replace USB cables when you want to power Arduino boards, such as this clone that I bought from a Kickstarter campaign. And while this connector is mini USB and this connector is micro USB, it's not a problem because I can easily change this cable after I open this USB charger up. What's interesting about this USB charger is in this shape it's not very useful for me because I don't have a car or an adapter to connect 12 volts to this connector. But I can of course open it up and remove and put wires directly on the connectors. What's nice is that because this USB charger has to support a wide range of input voltages, because the car may give you anything between, let's say, 11 and 15 volts. This USB charger should have a DC-DC converter chip inside, which may allow us to, as you can see, I'm not sure if it will zoom properly, let me see. Yes, 12, as you can see there it says 12 to 16 volt DC and 5 volt DC up to 0.45 amps. Of course, if you go and read the packaging on the back side, you will see here at specifications that it actually says 12 to 24 volts DC. So right away I know that it has a DC-DC converter inside because it has to accept a wide range of input voltages and output 5 volt DC from that. Well, of course it could use a linear regulator like this board uses here. As you can see, this board uses a linear regulator to accept let's say a 7.5 to 15 volts and convert using this linear regulator to 5 volts for the board if you choose to power it from this connector instead of the micro USB. Or you could make your own board like I did here. This one accepts anything between let's say 7 volts to 40 volts. But the problem with linear regulators is that they are less efficient and they heat up because the difference between input voltage and output voltage is dissipated as heat on this metal tab. So you need to put a heat sink and basically it will be larger than a switching regulator. If we open it up and see how it's made inside, we could use it to connect a 9 volt battery to the input and obtain 5 volt at the output with a bit higher efficiency compared to a linear regulator. So I already opened it up before just to make sure I print the datasheet for the chip inside in advance to make this video easier to edit. But I'm going to go ahead anyway and open it up in front of you. So right ahead we can unscrew this tab and we're going to see that the quality is not that great because just by opening up a couple of times already there are some problems with the plastic here. I'm not sure how well you can see it, but anyway. So this plastic is not that great, but if you don't open it up to change the fuse, it's not a problem. And by the way, this is a fast fuse but it's rated for 250 volts and 2 amps. So for a car battery, this would do basically, will offer no protection at all, so it's useless. So another negative point for this USB car charger. Even though it's a bit expensive compared to Chinese $1 chargers, the protection is lacking. So let's go ahead and open it up further. And I'm just going to use a screwdriver to pop it up. Okay, and here we have the car charger open up. And we have the two input connectors, input wires, plus and minus for the battery. And we have the MC34063 DC-DC converter, which is a very popular and cheap DC-DC converter. It's about 25 cents if you buy 100. And we have a diode, an inductor, two capacitors, and a LED to show you that it's running. And we have the cable for charging various stuff. And on the other side we should have a few small components, such as 3 resistors, 2 capacitors, and a resistor for the LED. Now if we go ahead and print the datasheet for this small chip, MC34063, we can see that, let's zoom in a bit. As you can see, it's a very simple chip. It's a 1.5 step up, step down inverting switching regulator. You can configure it in various modes. Naturally, in this board, it's configured as a step down regulator because it has to accept a wide range of input voltages and convert it down to 5 volts. And depending on what parts you use on this board, it's more efficient at 5 volts at a input voltage range. So they chose some of these parts, such as the inductor, to be more efficient, probably between 12 and 16 volts, but there's no reason why it wouldn't work at a slightly lower voltage or a bit higher voltage. The only limitations would be this input capacitor, which is 100 microfarads at 35 volts. I'm not sure how well you will be able to see it. So even though this buck regulator should support up to 40 volts, as it says here on this table, you can see here 40 volts, this input capacitor will limit the input voltage to 35. Just the same, this output capacitor on the board is rated for only 10 volts. So if you want to modify this circuit to change this resistor to get another output voltage, if you want to have an output voltage higher than 9 volts, then 10 volts, you should change the output capacitor as well. The datasheet is much larger, about 20-30 pages, but I only printed the essential pages. And this is the circuit for the buck, for the step-down converter. As you can see, they basically followed the datasheet, and we have the chip, we have the inductor, 220 microhenry. This may be a bit different. We have the diode, 1N5819. This is another diode, but it should be about the same specifications. I apologize. So the inductor, the diode, the chip. We have the small input capacitor, 100 microfarads, which is here, and we have a small output capacitor, which is 470 microfarad, 10 volts here. And on the other side, as you can see, on the other side we have here a C2, which is CT, the timing capacitor, which is about, I don't know, it's about 300 picofarads or nanofarads, I'm not sure. We have the two adjusting resistors, which is the 1.2 and 3.6. In this case it's about 1.5 and 4.7K, so it's just a different ratio, which outputs about 5.2, 5.3 volts, but there will be a small voltage drop on the cable. So by choosing a slightly higher voltage on the output, they're taking care of the voltage drop in the cable, and at the output there should be about 5 volts. And there's another small resistor, which is this RSC resistor here, probably. I'm not exactly sure because I didn't trace the circuit to figure out exactly where those resistors go, on which pins and so on. It doesn't really matter. And there's also a small 200 ohm resistor, which is basically just to limit the current going into this LED. So as you can see, it's pretty much the circuit in the schematic. This one accepts 15 volts to 25 volts and outputs 5 volts. It's really quite easy to figure out that this should work fine between 12 and 25 volts or even more. At lower than 12 volts we may have a problem in that the output current may not reach 500 milliamps, but we may have 100 milliamps at 5 volts from a 9 volt battery. Now let's go ahead. I'm going to go ahead and desolder this cable, and I'm going to solder 2 wires here, and I will use a small constant current load to test how efficient. Here's the constant current load, homemade constant current load. It basically accepts voltage from this connector and consumes power in this N-channel MOSFET here on this heatsink. So I'm going to connect this constant current load to this DC-DC converter and measure out how efficient this is at various input voltages and various current loads. Well, I have to admit this is somewhat unexpected, but as I was configuring this constant current load here on the desk, and as I started the power supply on 12 volts, not a few seconds later it basically popped up, exploded, and as you can see the output capacitor blew up, and here's it basically hit my arm. It was quite a surprise, but so I'm really puzzled, because as you can see, if you give me a moment, I'll start the power supply. So as I was saying, it basically blew up, and the reason for that is that the output, without anything connected to this USB charger, is actually 10.7 volts. Now I'm not sure if this is oh, let me show you actually. 10.7 volts, as you can see there. Now I'm not sure if this was a manufacturing flaw, because I really didn't change anything and there's nothing shorting out on the back side, or I didn't change any resistor on the back side. So I'm going to go ahead anyway and see if there's going to be a voltage decrease when I put this constant current load on the output of this USB charger. Just one moment. This constant current load will show a voltage on these two terminals, which is the same value as the current pulled from this board. So when I increase from this potentiometer, you will see the value increase on the multimeter. Just one moment. So we have right there 23 milliamps. So let's go ahead and put it at 250 milliamps, about the middle where this this USB charger should work. Is the maximum supported is 500 milliamps, and I'm going to use this other multimeter to measure the voltage on the output. Just one moment to connect the leads to it. This is not a very accurate multimeter on the voltage range, but it's within 1–2%, so it's really not a problem. Now, of course, this blown up capacitor, if it's not short circuit, it doesn't affect the circuit, so don't worry about it. But when I measure the efficiency, I'm going to replace it with a 470 16 volts or something like that. As you can see, 10.3 volts with 250 milliamps on the constant current load. And if I increase it further to, let's say, 540 milliamps, we see 9.8 volts on the output. So I'm really not sure what happened. I think it's faulty from the start. I'm going to turn it around and measure the resistors on the back side and see if the ratio here is correct for 5 volts. In this circuit we have 3.6 over 1.2 will give us about 3. So the output voltage is determined by the formula 1.25 times 1 plus 3.6 over 1.2. So it's 125 times 4. 3 plus 1 is 4. 125 times 4 is 5. So we have 5 volts out. So if I'm correct, the ratio between the resistors on the back side should be about 3. I'll go ahead and measure those resistors and we'll see exactly what's wrong on the back side. Okay, so I went ahead and replaced the input capacitor here with a 470 25 volt capacitor, as you can see there. And I also measured the resistors on the bottom side and came up with these values. So we have an R3 equal to 0.25 ohm, which is close enough to this 0.33 ohm, so that's fine. We have an R1 of 1.5K plus minus 5% maybe, so that's close to 1.2 kilo ohm, which is R1 here in this data sheet. And we have R2 4.572, which is about 4.7K plus minus 10%. So we have an output voltage configured to be about 5.07 volts. So I really don't know why we have 10 volts at the output, other than perhaps this step down DC-DC converter chip being faulty, because it would work out we have 12 volts at the input, 10 volts at the output. We have about 2 volts drop maybe on the Darlington pair inside the chip or a transistor. I'm not sure. At this point my bet is on the chip being faulty, and I have in the box of spare parts NCP3063, which is basically very close to MC34063. Just the 8th pin is not connected in the data sheet, but this one is actually not used in this configuration. So it's basically just connected to pin 7, so it doesn't matter that in our new chip it's not connected. So I'm going to go ahead and desolder this chip and solder one of these new NCP3063 and see what happens with the new chip. And here we are a few minutes later, after a bit of desoldering and resoldering of another IC here. We have the new NC P3063 soldered in place, and we're going to measure the output voltage on this output by connecting the leads here and turning on the power supply. And as you can see, we now have 5.16 volts at the output, so the chip was actually damaged. So I'm going to go ahead quickly and reconnect the constant current load on this new board, on the board with the new chip, and I'm going to quickly draw input voltage, input current versus output voltage, output current graph to see how efficient such a power supply can be compared to a linear voltage regulator. Okay, here we have the constant current load connected to the multimeter here, which will show the current drawn from the power supply from the USB charger. Here we have the voltage that comes out of the USB charger. On the oscilloscope you should see the voltage ripple coming out of the USB charger. We have about 157 milliamps from the 5.15 volts output, and as we increase the current, we can see that at 200 milliamps we have about 90 millivolts ripple. So our voltage hovers around 5.1 volts. As I removed my hands from the constant current load, we now see that it went a bit below at 22 millivolts ripple, 40 millivolts peak to peak. So as we go up, at 350 milliamps we have about 60 millivolts peak to peak. So it's quite okay for powering a Arduino or a microcontroller running at 5 volts. It's quite stable voltage. Of course the linear power supply would be much more smooth output, but this one is good enough. And if we go higher, at 450 milliamps, as the power supply was advertised, we actually see it improve a bit, and we have about 24 millivolts ripple. So at 5 volts, 450 milliamps as advertised, this USB charger works quite fine at 12.1 volts. It should go up to about 800 milliamps according to the datasheet of this chip. So at 600 milliamps we still have 5 volts at the output. And at 700 milliamps we still have 5 volts and everything is still quite okay. Let's go higher. 850 milliamps, it's still quite fine. And I'm only going to go as high as 1 amp. Well, actually you can see that, yes, at about 800 milliamps it's not enjoying it. So 755 milliamps, it's still fine. And here we are 20 minutes later. As you can see, I've disconnected this cable and placed the multimeter between these wires to measure the current. Then I've placed the current load and wrote down the numbers for various voltages on the input, and I came out with this sheet of paper, which I then copied into Excel, and here are the results. So as you can see, we have the current in 50 milliamps steps, more or less, and we have here on this graph the efficiency between 40% and about 75%. at various input voltages. On the top we have 9 volts. Let me actually write it down, 9 volts. And then the next line is 12 volts. Then we have 15 volts, 18 volts and 25 volts. So as you can see, the inductor and the diode were chosen in such a way that the DC-DC converter is actually more efficient at a slightly lower voltage than 12 volts. You can see here that at 450 milliamps the current is the efficiency reaches a peak of 75%, and then it goes down quite a lot to about 65-60%. On 12 volts we actually have a more or less stable efficiency of 70%, and at 15 volts and higher the efficiency is basically decreasing to as low as 55%. Oh yes, and one more thing that I forgot to mention is you notice that the efficiency is a maximum of 75%, and you may think this is bad, but if you think about it, when you have a linear regulator at any current amount, either it's 50 milliamps or 200 milliamps, the input voltage is 12 volts and the output voltage is 5 volts, but the current remains the same, and you basically waste the difference between input voltage and output voltage as heat. So you actually have an efficiency of which is quite lower than 75%. It's about less than 50% efficiency. I don't want to do the math right now. So if you use such a DC-DC converter to power your Arduino or whatever you want from a 9 volt battery, you can see that you have a 75% efficiency, so you gain quite a lot of battery life. Your battery will last longer, and your project will use a single battery for a much longer time. If you fine-tune the parts for this DC-DC converter, for example, changing this inductor with a smaller value inductor, then the efficiency or a higher value inductor, I'm not exactly sure. If you change the inductor for another value, you may gain a much higher efficiency at higher input voltages. So you may be able to put two 9 volt batteries in series to get 18 volts, and then use such a DC-DC converter to output 5 volts, but at a much higher efficiency of, let's say, 80% or 82%. And therefore your two batteries will last longer. You will have a much longer life for your project. And I have to mention that there are online calculators for this chip. You can search for this code MC34063 online calculator, and you'll find several programs that give you the optimum values for making a circuit to get the highest efficiency with the parts they recommend. For less than $2, the value that I paid for it, I got a very nice DC-DC converter. I also have a very nice mini USB cable, so I really can't complain, other than the fact that the chip itself was blown up. Here we have the simple, quite nice mini USB cable, which I can use for other projects. And I have to mention Dave Jones from EEV blog has a nice video about designing such a DC-DC converter, but in his video he makes a boost or a step-up converter using the formulas in this datasheet. and the circuit is similar to this one, but the diode is placed in a different to another pin, or laid out in a different way. But anyway, it's a very nice video to watch if you want to. Just search YouTube for it and you'll find it easily. Thank you again for watching this video, and I hope you enjoyed watching it and you learned something from this.